Okay, sorry everybody, I was chatting and I lost track of time. I guess is what happens when you start to chat. So we'll try and get started right away. Let's see. I guess people are starting to wonder about test 2. And I just started thinking about that myself, so I don't really have anything to tell you about the test yet. Other than I'm going to try and get some information posted by the end of the day tomorrow, get the practice stuff up, because I know the test is a week from Friday, so we're about a week and a half out. I'll let you know what the cutoff date is and all that stuff. Test 2, more or less, will be like test 1. Similar format, you can bring a sheet of notes, I'll give you a formula sheet. I'll have to confirm, but I expect we'll be able to write out in the lab again, because in here is just a little bit too crowded. So kind of any questions before we get started?
Is it going to be in class time again?
Yeah, in class time again. Yeah. So we are limited to that 50 minutes for just kind of stuff, right? And I know people come here from other classes, so we can't start early. And I know you're running out to other classes, so we can't stay late. So that 50 minutes is a tight restriction for us, unfortunately. Yeah, I wish I could give you all the time in the world, but.
No, that's kind of,
Yeah, that's how it
I
works.
need it during that time, so.
Yeah, some people find it helps them focus. I'm not one of those people. Yeah. Okay, so last day we did capacitors in parallel and some combination circuits, and we clued up by talking about energy, and that's where we're going to pick up today. Any questions about this stuff before we get going? Yeah.
Well, is that stuff going to be the cutoff for the next midterm, or is it going to be what you're covering right now going to be the cutoff?
I'm not prepared to commit to a cutoff just yet.
Okay.
Yeah, tomorrow. I'm not going to say something and then wish I changed my mind. Okay, so let's get started with some examples. One kind of circuit we use capacitors in, probably everybody's familiar with this. When you want to use a flash on a camera, so like on an a regular kind of camera like this, or even your phone camera, you get a huge amount of energy released in a short time. That's how you get that bright burst of light. That's a capacitor function, right? So there's a capacitor hooked up to that light. You need this large amount of energy to be dissipated, so you press your picture button. It releases the flash, and then it takes some time to charge up again. So that's kind of one circuit where you would see a capacitor storing energy. So in this question, how much energy do we have stored in a capacitor with a capacitance of 220 microfarads? If it's been charged to 330 volts, these are delta V. So we want to find the energy. Here we'll use our expression for energy. We wrote these down last day. And I had them down here on the bottom of my summary slide. So I know C and delta V, I'll use this middle equation. 1/2 times C times delta V squared. So 1/2 times 220 times 10 to the minus 6 farads times 330 volts squared gives us an energy of 12 joules, which is quite a lot of energy stored in that capacitor to be released over a very short time span. What is the average power dissipation? So pretty often we don't really care about the amount of energy, we care about how quickly it's released, and that's power, is rate of energy over time. So the power is the change in energy divided by the change in time. That's our 12 joules. That's how much energy is discharged in the flash. Divided by 1 millisecond gives us 12,000 watts, which is a very large amount of power. So that energy is very quickly delivered through that flash. Questions?
That summary slide that you show at the start of each class,
Yep.
is that particular slide in like the after class slides?
Oh yeah, everything I put up in class gets posted.
That's kind of,
Yeah. Yeah, those summaries are a nice way to kind of focus what we've done.
Yeah.
Why post them? Okay, so next example. So we talked about this a little bit when I brought in that Wimshurst machine. So lightning is a spark between the cloud and the ground. We looked at sparks between the two metal balls. Before we get a lightning, we do have a separation of charge because the cloud collects a lot of charge, the earth is charged. We get that huge separation of charge. That means there's an electric field between the cloud and the earth. If there's an electric field over some distance, that's the same thing as a capacitor. So you can think about the cloud and the surface of the earth creating a giant capacitor which stores up a bunch of electric energy. So that's what this question is talking about. So we're modeling our thundercloud and the surface of the earth as a capacitor. So we say that the charge center of a thundercloud, and what we're doing is we're assuming our cloud is like a big flat disk. Okay, so this is an assumption on our part. It's not a bad assumption. It's 3 kilometers above the surface of the earth. So here's the surface of the earth. So this means the plate separation of our capacitor is 3 kilometers or 3,000 meters. It contains 20 coulombs of negative charge. That is an enormous charge. Assuming the charge center has a radius of 1 kilometer, so that's our cloud, has a radius 1 kilometer, 4,000 meters. Take it as parallel plate, so it acts like it's a capacitor. First thing we want to do is let's find the capacitance of this system. So we remember our expression for capacitance. C is equal to the area times epsilon naught divided by D. Area means the area of the plate, so we're taking that to be like a disk, pi r squared, times epsilon naught divided by D. Epsilon naught, I'll write that over here on my list of information that I know. 8.85 times 10 to the minus 12 coulomb squared over newtons meters squared. So if we put all that in the calculator, we get a capacitance of 9.27 times 10 to the minus 9 farads. So this is kind of a typical capacitance. So this is a value we can have in our cloud earth system. We're next asked to find the potential difference between the charge center and the ground. So we'd like to find delta V. We know there's a relationship between potential charge and capacitance, so we can use that one. Delta V is Q over C. So we put in our 20 coulombs for our charge, 9.27 times 10 to the minus 9 farads for our capacitance, and we get 2.16 times 10 to the 9 volts. That is a huge potential difference. So that's really, really big. Okay, so there's a lot of potential difference between the cloud and the ground when we're building up to a thunderstorm. Part C, the average strength of the electric field. So we know we get electric field when we have a potential difference across some distance. The size of that electric field is delta V divided by the separation D. So we take our potential, divide it by our separation, we get 7.19 times 10 to the 5 volts per meter. So this would be a system that's right on the verge of a lightning strike. Lightning happens when we get the dielectric breakdown. That's about 3 million volts per meter. So we're getting close to a lightning strike here. And then last, how much energy is stored in this system? So we can use any of our expressions for energy. I'll use a half times Q times delta V. So I'll put in my charge Q, my 20 coulombs, times delta V, 2.16 times 10 to the 9. And we get 2.16 times 10 to the 10 joules. That's kind of a lot of energy. It might be hard to have a scale of how much energy that is. So to put it in context, I went onto the Newfoundland Power website and I looked up how much power does an average Newfoundland household use in 1 month. So an average household probably 3 or 4 adults, couple of pets, and people probably lazy about energy conservation, probably, right? Using too much hot water and all the appliances on all the time. So in Newfoundland, average power consumption monthly is about 1,300 kilowatt hours. That's kind of a funny unit. When you were in a high school math class, you probably learned how to convert that into joules. So a kilowatt hour, so kilowatt is 1,000 watts, so times 10 to the 3 watts. And then an hour is 3,600 seconds. So that average power consumption is about 4.68 times 10 to the 9 joules. So the amount of energy stored between the cloud and the ground is like 10 times what an average house uses in a month. So here's an idea for you. You want to solve some energy crisis? Figure out how to harness that energy, right? Take your lightning strikes, you figure out how you're going to build a system of capacitors and resistors to store all that energy and feed it back into the household. You will get a Nobel Prize. Okay, so not bad, there's something to work on. Okay, any questions? So one more example we can do. So the AED machines we see around, they have capacitors in them that store a lot of charge because we know we want them to deliver a huge amount of energy in a short amount of time, and that's the sort of thing we use capacitors for. So let's say we have an AED unit that contains a capacitor with a capacitance of 150 microfarads. It's charged to 2100 volts, so that's our delta V. And we know the plate separation is 1/2 of a millimeter. And we'll write that in meters. So find how much charge is on one of the plates when it's fully charged up. So what we're going to try and find for part A is what is Q. Remember, Q is equal to C times delta V. So 150 times 10 to the minus 6 farads times 2100 volts gives us a charge on each plate of 0.315 coulombs, which is actually quite a lot of charge. Generally, we deal with microcoulombs and nanocoulombs. So this is almost a full coulomb, so it is an awful lot of charge. What is the area of each plate? So here we'll use our expression for capacitance, which is A times epsilon naught divided by D. You can rearrange this and solve for A to find the area of the plate, of the capacitor. A equals D times C divided by epsilon naught. Put our numbers in. And we get kind of an interesting answer, 847 square meters. What do people think about this answer? So our AED box, go ahead and look at it on the wall, it's about yay big. Where do we put 847 square meters? Okay, so now we're talking about device construction. So this is sort of a true fact. The plate separation is about this, right? You can only get the plates so close together, and 0.05 of a millimeter is very close together. The capacitance needs to be about here because we have to have this amount of charge with this amount of potential. We don't have any choices. So how do we make a device that does that? So if we look at the expression here, and we think about the numbers we have, this epsilon naught, that's the permittivity of free space. It's how electric fields move through a vacuum. And of course, electric fields move through stuff as well, right? So here's one thing we can change. If we change epsilon naught by putting a material in there, then we change the capacitance. So that's one thing we can do. So if we can change this, it means we could have a smaller area. That also impacts what we could do about our D. So let's model our capacitor as a couple of foil sheets. So I just cut off a couple of strips of tin foil from my office. If I want to make my capacitance bigger, I'd like to get these plates close together. I can't let them touch because they're conductors and the charge would just flow from one to the other. If I don't want them to touch, I could take a really thin strip of something we call a dielectric and put between the plates. That dielectric is going to serve two purposes. It's going to keep the plates from touching so they can be even closer than that value D. And it's going to increase the size of the electric field between the plates because electric field travels differently through a material than through a vacuum. Okay, this is still pretty big, right? And it's not nearly 847 square meters. So what I can do is I can put a couple of strips of insulator on the inside so that the charge is not going to flow. And then I can do this. Now my capacitor is getting a lot smaller. So this is how they make capacitors. They put a dielectric between the plates. They make it as thin as they can possibly produce. They put the two metal plates together, and then they roll it all up tight, and then you can squeeze a huge amount of area on the plates into a small physical device. So people who are interested in device making might find that sort of thing interesting. I find that neat. Okay, any questions? And the dielectrics is not something we're going to study, but it is good to be aware that that sort of thing can be used.
So that charge we found A, that is technically the charge after all of the available potential from the potential source has been moved to that, or the capacitors.
Yeah, essentially we take that capacitor, we hook it up to a 2100 volt source, we let it flow until it's fully charged, and that's how much charge would end up on the plate.
Okay.
Yeah. Okay, last bit, how much energy got stored in that charged capacitor? So we'll use our expression for energy. A half times C times delta V squared gives us 331 joules. Which is a lot of energy, but if you want to start somebody's heart pumping in a regular rhythm, you have to give it quite a shock to a system, so you've got to put a lot of energy in there quickly. Okay. Questions? No? Okay, looks like we're good to keep going now. That takes us to the end of chapter 24, and now we're ready to start chapter 25. So that's going to be about current and resistor circuits and RC circuits, so lots of interesting stuff. Chapter 25, reading through the textbook, it kind of has a lot of words and a lot of explanation. I'm going to hit the highlights in class, the important parts to know about how circuit works and kind of where resistance and all this stuff comes from. If you're looking for some deeper stuff behind it, you'll probably want to go ahead and read the textbook, but I'll kind of get all the important stuff here. So in this chapter, we're going to start talking about electric circuits. They contain charges in motion. So until now, we've talked about conductors and electrostatic equilibrium. No charges are moving. Now the charges are going to get moving. That's equal to a current. And when current moves around a circuit, we're going to start talking about circuit devices. So we get energy flowing around a circuit. Circuits are really important because kind of all of the devices you have are full of circuit boards. And another neat thing that is full of circuit boards is your actual body. So like your nervous system is one long electrical circuit that kind of transmits energy all through your body. So there's lots of biology stuff in here too. Even though that's not really what we focus on, but it's cool that it's there. So let's go back very briefly to what we discussed for a while, conductors and electrostatic equilibrium. So when we covered that topic, we said there was no electric field inside the conductor, and that's certainly true. And we said that the charges inside the conductor don't move. That's not exactly true. So atoms and molecules and electrons and protons, they're all inside a material, and they're all bouncing and wiggling around. Everything moves a little bit. Nothing is perfectly still. So if we zoom in on a charge inside a conductor, if there's no electric field, if we look at the blue path here, the electrons are gonna bounce around. They're gonna bump into neighbors, they're gonna reflect off, like a bunch of people in a hallway, just sort of fidgeting and moving around. But ultimately, they won't go anywhere. So all of the motion is random, and eventually, they ultimately don't move left or right. They just kind of stay wiggling about the same spot if there's no electric field. If we take our wire and we put a potential difference across the ends of a wire, and that's certainly something we can do. We can take our wire and we can connect it to the two terminals of a battery. Positive, negative, potential source. So that 100% is something we can do. If we take our wire and hook it up to a battery, we create a potential difference. If there's a potential difference spread over some distance L, that means we're going to have an electric field in the wire. So we can put a field in the wire. That electric field E is the potential difference divided by the distance, which I labeled the length. So then what happens is every electron inside the wire will feel an electric force, right? Because we know force is Q times E. So the motion of this electron, it is going to be bumping around, running into its neighbors, but overall, because there is a force that points to the left, it's ultimately going to move to the left. Okay, so because of that force, it will move to the left. And we say that it moves with a speed vd called the drift velocity. So the electrons will move because of that force. And that's represented by this red path. So it starts in one place, bumps around a bit, and ultimately it ends up a little bit more leftward than when it started, or a little bit more rightwards than when it started. Okay, so far so good? So that's kind of how we get charges moving. We connect it to a source of potential, which creates an electric field, which creates a force, which makes it move. So that's how we get it going. Probably important to point out here that electrons overall are not the only kinds of charge that move. So when we have conductors, it is the electrons that move around in conductors. But other charges can move, and we call those things charge carriers. So when we have a plasma, it's not electrons that move around in a plasma, it's actually ions. So charged ions move around in a plasma. And semiconductors, this is really neat. The thing that moves in a semiconductor is called a hole, and it's actually the absence of an electron. So that's kind of fun. You might like Physics 3000 if you kind of like some of that semiconductor stuff. Okay, so questions here about the nature of this. Your book talks a lot about this drift velocity and how you figure it out. I think it's enough for us to understand that there is a drift velocity because of the applied force. So let's talk about the motion of those charges a bit more. Yep.
Sorry. So are we saying that a wire is a conductor?
Yep.
Okay.
It's made out of copper, right?
Right.
Yeah.
There's like, okay, what are the two walls? Like, what are the two plates?
What do you mean the two plates? You got me lost.
Bro, I'm so sorry. I'm thinking a capacitor. I was trying to understand why we're considering a wire like a capacitor, but that's not the case.
Okay.
So my bad.
All right, no problem. Yeah. Okay, so, did you call me bro? That's so funny. I don't think anybody ever called me bro before. I love it.
Well,
This is a good day.
welcome to the club.
Bro. Okay, so those moving charges, that's electric current. Okay, so when charge moves, that's what we call current. Might be interesting just to stop for a moment and think about how charge actually moves. So when you have a wire, it's full of a bunch of charges, and those charges can move. If I had a wire the length of this room, the electron on that room wouldn't physically move to the electron on this wall. So one electron there doesn't go there. What we have is a whole wire full of electrons, and they all move forward a little bit. Like a tube full of marbles. When you push on one end, the marble at the far end falls out. Or a garden hose that's already full of water. As soon as you turn on the hose, water spews out. But it takes a while to get from the house to the end of the hose. So that's kind of what happens. It's all full of charge, and as a whole, they kind of move as a single unit. So an electron here at this end all moves forward, and it's the one on this end that comes out. Kind of think about it that way. How well that charge can flow depends on a bunch of things. It depends on the density of the charge carriers, so how many electrons are in the wire. It depends on the size of the charge itself, so electrons have a different charge than some of the positive ions in the plasma. It depends on how fast they're moving, and it depends on the area of the conductor. So how the charge moves, the current actually depends on a bunch of stuff, and again, all those details are in your textbook if you're interested in it. So when we talk about electric current, it has a symbol, mostly of a capital I, and sometimes it's a lowercase I. Your book goes back and forth. I kind of pretty routinely stick with capital I, but you may see either. The units of current are amperes, which is often just said as amps. And amperes has a symbol, the unit symbol is a capital A, and that's after André-Marie Ampère, a French physicist from the late 1800s. The definition of our current, it's the rate at which charge passes through a surface with area A. So how much charge passes through an area? Our average current overall would be the total charge that flows divided by how long it takes. And then often we're interested in the instantaneous current. So not what happened over an hour, but what's happening right now. That instantaneous current is still the change in charge over the change in time, but it's a little bit of charge over a little bit of time, or the derivative. So if you have an expression as a function for your charge, you take the derivative from the function for your current. Here's where your book gets a little bit wonky. Your book, kind of in the same breath, says that current flow has a direction, and then it promptly follows with current is not a vector. Those two statements don't match to me. So things with direction are vectors. So I will stand by that statement. I think that is the definition of a vector. I'm not sure why your book disagrees, but it does disagree. The flow of current, the direction of current flow is whatever direction a positive charge will move. So the direction of current flow is however a positive charge will move. This is a historical definition of current flow. Way back when scientists were starting to study currents and circuits, they did not know about the existence of the electron. So as far as they knew, a thing that they called positive charge was moving because they didn't have the means to recognize that it was a negative charge moving. So that's why they defined it as the direction of flow of a positive charge. I think in high school physics, you often talk about how a negative charge moves, which leads you to doing things like a left-hand rule. At this point, you'll leave all of that behind. From now on, we'll talk about current flow in this direction, and that leads us to right-hand rules, which we'll get into when we start our magnetism chapter. One last thing about current flow. We have two kinds of current. So you can have DC current, so that's a direct flow. That's what you get when you hook up to a battery. You can also have AC, which is alternating current. That's what you get when you plug things into the wall. We should get to AC kind of right at the end of this course, but DC is what we're going to stick with for at least a little while. Okay, questions? So back to our lightning, and a picture I took off the NTV website at one point. So during a lightning strike, we can get a current as large as 25,000 amps, and it can last for about 40 microseconds. How much charge do we have in that lightning strike? So that's kind of an interesting question. So we said that our definition of current is change in charge divided by change in time. That means the net amount of charge that flows is the current times how long it's flowing for. So 25,000 amps times 40 times 10 to the minus 6 seconds equals 1 coulomb. So a lot. So lots of charge will flow during a lightning strike. Okay, still good? a very interesting example. So, on to our next bit about current. So we said that current was the amount of charge flowing through an area. That takes us to a new definition, and that definition is called current density. Current density is pretty interesting. Current density has a symbol of J, and current density is the amount of current divided by area. So current density J is the current divided by the area. It will have units of current divided by area, so amps per meters squared. So that's a new definition. We're going to use this one. George Ohm, a German experimentalist around 1800, he studied a lot about circuits and potential and current and resistance and all this stuff and current density. So in his experimental studies, he found that the current density, so in a material object, so in some metals and things, was proportional to the electric field within the object. So this was an experimental result that he found. It's maybe important to point out at this point, this is not true for everything. This was only for certain materials, and those materials are things we call ohmic materials. So lots of things like semiconductors and diodes and LEDs, they don't follow this rule at all, but ohmic materials like metals do follow this rule. So current density is proportional to the electric field, so we can write it as an equation with a constant of proportionality, sigma times the electric field. And this expression is called Ohm's law. Your book here, when it comes to current density, it now decides that current density is a vector. Again, to me, that kind of says that current has to be a vector. So density is a vector and current is a vector as well. This sigma here, this is called conductivity. So the constant of proportionality is called conductivity. Conductivity has units of amps divided by volts per meter. And it's a measure of how easy it is for current to flow through a material. And it's a property of the material itself. So all copper, all pieces of copper will have the same conductivity. All pieces of aluminum will have the same conductivity. So it's a material property. We also define a new quantity that has a symbol of rho, that's 1 over sigma, and this is called resistivity. So it's just the inverse of conductivity. Resistivity has units of volts times meters divided by amps. Conductivity is a measure of how easy it is for current to flow. Resistivity is a measure of how difficult it is for current to flow, okay? So kind of like opposites. If rho is 1 over sigma, then it means that our electric field is rho times current density. So kind of same thing, same measurement of a thing. Questions? If I assigned all of this stuff as reading material before class, how many people would actually do it? Please be honest. A small number. Okay, it's one of the kind of ways I've been seeing about in teaching seminars, and I often wonder who would actually do it. Okay, so let's talk about this stuff a little bit more. So the ease or difficulty of current flow through an object. So conductivity and resistivity, they're the ease or difficulty of flow through a material. Now we define resistance. And resistance describes the ease or difficulty of flow of current through a particular device. So conductivity and resistivity is about the type of material. Resistance is the object itself, so it's going to depend on the size and shape and what the material is made out of. Resistance has a symbol of a capital R, occasionally a lowercase, but almost always uppercase. The units are ohms after George Ohm, and that has a symbol of a capital omega. And 1 ohm is equal to a volt divided by a meter. So now what we'll do is let's take our thought of resistance, let's take our Ohm's law that we wrote down on the previous slide, and let's get to the more familiar form of Ohm's law that people probably remember from high school. So current density, J, is the conductivity times the electric field. And remember, that's an experimental result that George Ohm found based on certain materials, called ohmic materials, but not all materials. Sigma is 1 over the resistivity rho. So we can rearrange to find that the electric field is the resistivity times the current density. Okay? An experimental result that shows one is proportional to the other. The magnitude of the electric field E then is the resistivity times the magnitude of the current density. We might remember here that electric field is potential difference divided by the separation between the two ends, and current density is the current divided by the area. So let's put these two things in this equation. V over L equals rho times I divided by A. Now I'm going to cross multiply my L up. V is equal to rho times L divided by A times the current. Then we define, or we recognize, resistance is rho times L divided by A, which means we finish with V equals resistance times current. So I'll say that this is also Ohm's law. And really, it's just our last expression expressed in a new way. They say the same thing. So this resistance depends on the resistivity. Remember, that's a material property. But it also depends on the length and the cross-sectional area of the device. So the size and shape of a device matters. So good? Okay, let's do an example about resistance. So I tried to introduce a tiny bit of lingo here. An 18 gauge copper wire. So when we have the gauge, that tells us the thickness of the wire. And what you do when you want to figure out how does gauge correspond to thickness, you typically just look that up in a table. I guess some people might remember, but I would not be one of those people. So if you have an 18 gauge wire, this tells you what the area of that wire is. When I wrote down my area, clearly I made a typo. It is not 10 to the plus 7 square meters. It is 10 to the minus 7 square meters. Oh, sorry about that typo. So our copper wire has an area of 8.20 times 10 to the minus 7 square meters. It is carrying a current of 1.67 amps. We'd like to find the electric field and the potential difference if we have a length of wire that is 50 meters. We'd also like to find the resistance of that bit of wire. So there's all the stuff that we know. Let's start by finding the electric field. Probably there are some different ways to go about this. I'm going to start with remembering that electric field is the resistivity times the current density J. For my resistivity, I know that it's copper wire, so I can look up the resistivity of copper in a table. These numbers are not something I would expect you to remember, and I also wouldn't really expect them to I wouldn't expect you to put those on your equation sheet. I would give you these kind of values in a test, or I would give you the table to look up. so my electric field is resistivity, which I know, times current density. Here I remember that current density is current divided by area. So I've got 1.72 times 10 to the minus 8 ohms times meters times 1.67 amps divided by 8.2 times 10 to the minus 7 square meters to get an electric field strength of 0.0350 volts per meter. So there's my electric field in the wire. Part B, find the potential difference. Again, different ways to find the potential difference. I'm going to remember that E is the field divided by the distance. Oh my goodness, sorry. Electric field is potential over distance. That means potential is electric field times distance. Sorry about that. So times 50 meters. Gives me a potential difference of 1.75 volts. And then last, what is the resistance? Again, different ways to find it. We could go with R equals rho times L over A. So we know rho, we know L and A. Or we could use R is equal to the potential divided by the current. Either of those are fine. They should give exactly the same answer. And we get 1.05 ohms. Mostly what we're doing in this chapter is setting the stage of what we're going to need to understand to do the next chapter. So we're not doing tons here, but we're looking at the basics. Okay, so next, let's look at the details of what's going on inside of an actual battery. So when we talk about a battery, and it can be any kind of battery, so I got a little one here just to back up for the mic packs that I have to use. So a battery is a battery. It's got your two terminals. When you buy them, it's got a potential stamped on it. So we're going to look at those things next. So inside of a battery, probably you've seen old batteries that kind of get a bit crusty on the outside. Just some of the chemicals inside be leaking out. So inside of a battery, it's full of chemicals. The chemical reaction inside does work to move a positive charge towards the positive terminal. So that's what's going on inside the battery. So we get a positive charge, the chemical reaction does some work, and it makes that charge move. So that's what happens inside of the battery itself. It does work to make it move, and then we get a separation of charge, because if the positive moves up, means relatively there's a negative on the bottom, so there's a separation of charge, which means we have an electric field inside the battery. So the positive is up, the negative is down, so our electric field points up to down. If there's an electric field inside the battery, then there's going to be a potential difference between those 2 points, because field and potential are related. So we'll get a potential difference between here and here. So I might call my terminals A and B. And the potential difference between A and B, we might call V, A, B. So the charge is moved, gives us a separation of charge, which gives us an electric field, which gives us a potential difference between the two terminals. We know electric field goes from high potential to low potential, so we could put that on our picture too if we wish. So this one is high potential, and this one would be low potential. So tying together some stuff we did in the previous chapter. And then we know that charge is going to start flowing around the circuit. So the positive charge comes out of the terminal, goes into the wire, comes around the circuit, and our flowing charge is called our current. So we'll label that I. So we get a current flow. What else? Now we get to something maybe you did in high school, maybe not. the potential difference between the terminals inside the battery, so that refers to the ideal amount of potential difference a battery could supply to a circuit. It's kind of the amount of potential you're supposed to have if your battery is perfect. That potential difference inside the battery, so between the terminals inside, that's called EMF, and that has a symbol of epsilon. Historically, EMF was called electromotive force, and this was coined back when they didn't understand what was going on. It was before they discovered the concept of a potential difference. They thought it was a force, but really it's a potential with units of volts. So we don't say electromotive force anymore. It's a complete misnomer because it's not a force, it's a potential. So we just say EMF. Okay, so far so good? All right. So then our potential difference between these 2 points, the potential difference across the wire, so from A to B outside here, for an ideal battery is going to be equal to the potential difference supplied by the battery. So in an ideal battery, where there's no resistance to the flow of charge inside the battery itself, so it's absolutely perfect, there's no energy loss, this potential between the terminals would be equal to the potential we're supposed to supply. So that's related to the amount of energy, the amount of work the battery can do. A real battery is a little bit different. Oh, and this would be equal to the current through the wire times the resistance of the wire from our own law. So that's our ideal battery. A real battery, sometimes there is a little bit of resistance to the charge flow inside. Starts to get old, starts to get a bit crusty, the battery doesn't do its job the way it's supposed to. We get some internal resistance to the flow of charge. So when that happens, we get an internal resistance to the flow of charge. We call that internal resistance a little r. Then the total amount of potential that we can get on the outside of the battery is what it's supposed to supply, epsilon, the ideal amount, the EMF, take away the potential lost due to what's happening inside. Okay? So what we actually output is what we're supposed to have, minus losses due to the internal resistance. So that's what this expression is telling us. Okay, and then one last little conceptual thing. If we had, and then this is equal to I times R, what if R and R equals 0? So if your wire was ideal and had no resistance, if your battery was perfect and had no resistance, and you hook up that wire to the battery, what you're going to get is an infinite current. And that's a short circuit. When that happens, say you hook up your car battery to some wires with no resistance, that's when things catch on fire. So your current gets really, really large, starts to spark, starts to smoke. That's when you get fires. So you would never, ever make a short circuit. Okay. That took us right up to time, so we'll quit there. Remember, we are back tomorrow, because tomorrow, even though it's Thursday, is actually a Friday for your month schedule. So we're in tomorrow.